Okay, let's welcome Ruben for the second advanced lecture. Thank you.
Should we use the mic? Can you hear me well? Yes? Okay, perfect. So thank you for being here after watching the match tonight. Like me, all of you woke up at 3 a.m. to watch the match, so I see that you are pretty awake. So these are the slides I have to show. Also because they speak about the young generation. No? So you know that this is Lamin. This is 2 days ago he was 16 years old, and since yesterday he's 15. So his father is from Morocco, his mother is from Ecuador. So he's a very smart player. So he sees that here there is an opening. So and he sees that this guy running like hell. That's Nico Williams. His parents came all through Africa to Spain. So this guy get the ball, and he finally scores. So that was the first goal tonight, and after that it was a huge success. So, okay, so let me talk about now science. So all of us in this room are interested in this question, and Nilon has been describing this in very nice way, so I'm going to repeat this. So all of us are interested in the question of how neural circuits, generate behavior. That's the basic question, how these two things relate to each other. And there are two main approaches. One is what we can call the bottom-up approach. This is the idea that you start to record, to get all the data that you can, all the morphology of neurons, all the details that you can. And the idea is that if you have enough details, maybe a priori you can put all these things in a big simulation, simulate this, and then magically, hopefully, some emerging interesting behaviors will arise from this big simulation. Of course, it has been like a major failure so far, because well, we don't have enough information. But that's not the main point of this, of taking this approach too seriously. The big issue of this approach is that there is maybe too much emphasis on data collection and in simulation, and very little emphasis on theory. So that's the first bias that you have when you really believe only in this alternative. And the second bias that typically arises in this approach is that there is very little emphasis on behavior. So behavior remains something that is going to emerge eventually from what I'm studying, but it's not really the focus of And of course, there is this other approach, which is a top-down approach, which comes again with a lot of data. I mean, this top-down approach is not a theory-driven approach in a sense. It also comes from data, but data coming from behavior. So we know a lot of behavior, a lot about behavior. We have studied, the pathologists have studied behavior for several centuries now, so we know a lot of behavior. And not only that, our perceptual system is highly tuned to behavior. So if we see an artificial agent behaving, we can tell right away if that behavior is realistic or not. So we can use this information to also instruct or inform models as to how should explain and relate neural circuits with behavior. Okay, so I started my first lecture with a question, which is asking which of these two agents would you a little bit more realistic. And of course, the answer is not completely unambiguous. But if I ask you which looks more energetic, more lively, some animal, or if you give a poll to your niece, after experiencing a while with the poll and getting bored with it, what your niece will do with the poll? This behavior on the top, so I'm clicking always the wrong button, this behavior on the top of this one at the bottom. And I think that many of you agree that there was the one at the top. But let's get back to this. So what you perceive in the top again, a little bit of more realism. And the reason that I think is that life is in motion. And actually you can define life as something that moves. This is one of the most important features. Indeed, natural agents have a natural tendency to move around and interact with the world, unless we get very old. But not in order. I'm going to get back to that. So 100 years of research in developmental psychology have shown that kids interact with curiosity in the world. And one feature that I like and I find quite surprising, that is even after heavy training, there is a lot of variability in the behaviors that you display. And this is something that seems to be inherent in all types of behavior, even after overtraining and becoming experts in certain activity. And the reason is why we have these features of behavior. And the common account is very standard, it's very clear. It's like, if you have variable emotions, if you interact with curiosity in the world, then you can learn. And if you can learn, you can get higher feature rewards. So that's the standard account. And this standard hypothesis pervades all the fields of knowledge, mostly psychology, economics, neuroscience, and artificial intelligence. So this is the idea that animals are, we have defined this in the previous lecture, extrinsic reward maximizer. So there is a utility function that is being optimized by these agents, and this utility function is given by nature and cannot be changed in a sense. But I'm going to start today my presentation by asking now seriously whether we are a utility or reward maximizer. So I don't know if you know this example of this vacuum robot, cleaner robot. It was working it was cleaning in the room of a hotel. It escaped. It was lost for 1 day, and it was found outside the hotel under the buses the day after. So this type of unpredictable behaviors tell us that designing artificial intelligence agents with a reward function, providing a reward function to this agent is a very hard problem. It's a very hard engineering problem, right? So let's think just 1 second about this question. So you're now an engineer, and you want to embed this agent with a reward function. You're essentially telling this agent what to do. Well, you can ask this agent to collect as much data as possible. That's, of course, going to be one important role of this agent. Or you can ask it to focus on a specific type of task with allergic content. Or you can ask it to be energetic efficient. Or you can perform any linear combination of these features. And as you can see, this is totally arbitrary. So how do you set this parameter? So from the engineering point of view, giving a reward function to an artificial agent is a very hard problem. But if you're interested in natural behavior, the inverse problem is also very hard. So if you're observing behavior in an animal and you want to infer what was the reward function that better explains the behavior, that's typically a very, very hard problem and very often imposed problem. So in my postdoc, we estimated the cost function in a accumulation task, the type of task that Tianmin has been describing, and we were successful in estimating what was this reward function, this cost function. But I should say that it was possible because there was a very simple experiment. It was a binary task with full control on the stimulus and so on. Now imagine what would be the task of inferring the reward function or the cost function if now you observe an animal in the wild. It's going to be a really very hard problem. So we have to take a different approach, at least complementary to this one. So what I'm going to propose is to theorize about this problem and trying to figure out what could be intrinsic motivating goals for natural agents. And think about that. So this is going to be my proposal for today. My proposal is going to be, let's abandon the idea that we are reward maximizers and that we move around and interact with curiosity in order to maximize the reward. Let's abandon this idea and let's adopt the opposite idea, which is the ultimate goal of intelligence is moving around, generating behavior, occupying space, and rewards is going to be just the means, rewards understood now in the sense of sugar, proteins, building blocks, those are going to be just the means that we need to accomplish this goal of conquering space. Okay, so these are very wild words, so we need to formalize this somehow. So I'm going to propose this principle, and this is going to be just a summary that I'm going to unfold. So I'm going to say that agents maximize something that we call the occupancy of actual state path space. I'm going to unfold this for you. So you don't need to understand every single word of this sentence right now. But, that's going to be my program for today. And we're going to call this maximum occupancy principle mod for short, just to remember it easily. And there are two papers, I think that you cannot see because of the projector, but you have in the previous slides where you can get this information from. So before I show you the theory and a bunch of simulations, let's think just very briefly about what type of behaviors will result from this principle. Okay? So the first obvious outcome of this is going to be that your agent is going to be naturally curious and explorative. It's going to move. This is by construction. This is not a surprise. In this theory, these agents still are going to seek reward in order to be able to move more. Okay, so they still need energy, they need building blocks to keep moving. So rewards are going to be still important in this framework. These agents are going to have survival instinct. So they know if they die, they cannot move further. And because the goal is moving further, occupying space, spreading energy, they're going to tend to avoid terminals. They're going to tend to avoid dangerous situations if it's not necessary. So they're not very risky agents in a sense. Of course, they're going to have a preference for freedom, in the sense that they're going to like to be in states and perform actions that promise very large number of future states and the possibility of future action. So they would like to be in these open spaces, like the pass of Lamin to Nico.
So,
yes, either way.
does this assume that the animals know all the possible states, all the possible actions they can take in each one of the states, or can they learn this on the go?
We're going to be thinking about different levels. One, it can be like evolutionary level, where many things are going to be embedded in priors. So, meaning that the agent doesn't need to do this computation. But there are going to be some inductive priors that are going to tell, okay, these are good things to do. And I believe that this is going to be one important component in this framework. But there is also the second component of inference and learning that, of course, that's going to work on a smaller space set of some smart representation of the state space, not the full fit. So here we're going to play with many different time scales, in a sense. I'm not going to be just married with a particular time scale. Yeah, you have a question.
Yeah, so you're doing great seducing us with these nice things, but two things. First of all, this would say that we would just move our muscles randomly, for example.
No, not necessarily.
Second, so this, for example, it would mean that the mouse would move everywhere in the room, which is not what you see. The mouse stays close to the walls, for example.
Right.
Now, second thing is, if you have the possibility of dying, that's a very strong loss function. So you're including actually a loss function.
There is a loss function, but it's very distant. So it's like very sparse information.
Like the cheese in the mazes for Nathaniel and now.
In a sense, yes. But here the program that they propose is that these terminal states are going to be pretty general. In a sense. So once we figure out what these terminal states are, they're going to be generalizable, so you can generalize to different situations. Well, in the other setup, essentially you have to infer a priori a new reward function for every situation. So here the terminal states, the idea is that they are much sparse in that sense. So there are very few terminal states that can shape completely the behavior of the agent. But just bear with me. I'm going to show and explain things like what you said at the beginning. These agents are going to be capable of deterministic behaviors when this is needed. And of course, if you move your elbows and joints too much, then you're going to have deterioration of the elbows and the joints, and then you cannot move that in the future. So there are going to be some biases embedded in your brain, making that you don't do this too much. Yes?
I just wanted to ask a quick follow-up if this model could maybe explain to the smallest, like in an evolutionary sense, but then it's like against it doesn't bring it close, like twitching, things like this that might not really hinder your ability to get to that reward or that.
That's interesting. So Yeah, let's talk about that offline. I think it's a good idea. I didn't think much about that, but I think it's a good idea. Yeah. More questions? Okay, so preference for freedom. I promise that I'm going to relate this with neuroscience, and the important indication here is that this theory predicts why neural activity is so variable. So variability in the brain is going to be actually a goal. And not surprisingly, because variability in the brain is going to be connected with effectors, with the body, and if you want to generate complex behaviors, you need to have complex neural dynamics, and these two things go hand by hand. Okay, so, well, this is the summary about Markov decision processes. So you have the last chance to ask any question, if you want. But I'm going to use this slide just to remember you the standard account. The standard account is that there are states, transitions, but there is this extrinsic reward function. And this extrinsic reward function, that is going to be a function of the state and the action, is the quantity that is typically being maximized. And remember that we define this value function, which is the expectation over the sum of future extrinsic reward. And this is the quantity that ought to be computed, because this defines fully the policy, as Professor Yoshida explained yesterday. So how do we model the idea of occupying action state space? So let's replace the extrinsic reward function by this intrinsic reward function, capital R. So what should be the properties of this capital R? So let's start with a deterministic policy. And let's think just about the actions that you can perform in this particular state. So remember that there is this policy, but now let's assume that our policy is deterministic, meaning that there is only action that we typically perform when we are in this particular state. And the question is, what is the occupancy gain? So how much new occupancy of actions, states, we gain by performing always the same action? So intuitively, the occupancy gain is 0, because we always performing the same action, so we are not gaining any new occupancy, right? So this is one property that we want from this intrinsic reward. So let's try this, and I'm going to formalize this later, but just now let's try this. Let's assume that this intrinsic reward function is the minus logarithm of the policy. The policy surprise, in essence. So this quantity is going to obey this property. So if the policy is deterministic, the probability of a specific action given S is equal to 1, and the minus logarithm of 1 is 0. Okay, so under the deterministic policy, the occupancy gain is 0. But if you perform an action with very little probability under your policy, that's going to be a small number. When you take the minus logarithm, that gives you a big number. So whenever you perform a very unlikely action on your policy, you get a boost of intrinsic reward. Okay? And so this is the occupancy gain. Now we can define the occupancy itself, the action occupancy, which is going to be the expectation of this. And if you do just a little bit of math, you realize that this is the action entropy. So on average, the occupancy is equal to the action entropy.
So this is for discrete actions.
This is for discrete actions. But you can generalize also for continuous variables, except for a baseline that will define the fine graining of the actions. So now let's go to the transition to the state. So you perform one action, and there is a transition to a new state. And let's assume that my policy is deterministic and the environment is also deterministic, meaning that if I'm in this state, I always perform the same action, and if I perform the same action, there is always a transition to the same state, again and again. So intuitively, what would be this is what I'm saying, what would be the occupancy gain of this action state? Now there is an action state transition, with an action and then a state. The occupancy gain by performing this action and observing this transition state is 0, because I'm doing this again and again. So again, intuitively, the intrinsic reward should be 0. And what quantity has this property? Well, the minus logarithm of the joint probability of the policy, the probability of the action, and the probability of the transition. Okay. So now you define the occupancy as the average of this. Then you have two contributions. One is the action entropy under your policy, and the second contribution is the state transition or surprise, state transition surprise. Okay, so now we can replace the standard value function in hard RL with a new value function, which is going to define the full goal of the agent. And the full goal of the agent is not maximizing immediate occupancy, but is maximizing the occupancy from now up to the future. So we're going to define this value function, which is going to be the expectation of the sum of features, action, and state occupancy. So the agent should care about not being alive and generating a lot of movement right now, but also about being alive and generating a lot of movement in the future. And this is where you can have a trade-off between deterministic behaviors right now, like coming here and sitting down over here and listening to me, because you're going to learn something that in the future is going to give you the opportunity of performing many, many actions and going to many different places and talk about these interesting ideas with your colleagues. So, yes. And then we can put a weight, and we can generalize. Actually, we did that in the paper. Yeah, it's straightforward to generalize it. And the whole theory works for an arbitrary weight, even negative weights, actually. Okay, so why this quantity? I mean, so far I have been using the hand-waving argument to argue that this is a relevant quantity to be optimized, and there is a very deep reason why we want this quantity to be optimized and not other one. So if you're interested in a measure of occupancy, and you want that this measure is additive, meaning that if you split a path into two components, and you want to define the occupancy of the full path, if you want the additive property means that the occupancy of the full path should be the sum of the occupancy of the first part of the path plus the occupancy of the second part of the path. So since you have some additive property that you want to embed into this measure of occupancy to have some rational properties, otherwise it would be a little bit weird quantity. And what we can show is that this sum is the only choice. Adding some coefficients, as Vincent said, that's the only choice that you have. Yes?
When you say that it's the only measure, are you saying with respect to other oral models? Or?
It's the only measure that captures the idea of occupancy and has this additive property. I'm going to go and explain the properties that I'm going to enforce for this one. Okay, so let's start with a very simple tree, decision tree. And here my nodes are going to be action states.
In the absence of any additional constraints, this would just give uniform.
Yeah, Ronald Walker would be the optimal agent.
Well, uniform over actions, uniform over transitions. Okay,
so yeah, to shape the behavior, it's important to have terminal states. That's going to be one important one. Yeah. Yes.
So you can have states that are not uniform in how they progress in the future. If you have two paths, one with more states than the other.
I'm going to give you plenty of examples of that in the next slide. Yes, Veronica.
Does the series like specialization include division of labors? As or maybe it's allowed for some people to specialize in the state.
Right. So we want to take this principle to multi-agent settings, and the idea is the species or the group of population would like to maximize occupancy, for example, like conquering, like going to Mars, or something like that. So how this population should prepare to keep exploring and occupying space. Then we don't know yet what the results, the outcomes for this algorithm will be, but things like specialization will be like something that will probably emerge. Also communication and very interesting agent-to-agent interaction, but we didn't explore yet. But these are very, very important directions that we want to take action. Because we can generalize very easily to that situation. More questions? Yes?
You said that additive can be a good thing, but I sometimes imagine, right, if I already know that I've been to a few places and I want to explore other things and I haven't done, I want that kind of history behind it.
Well, that would be this is because you change the policy. So once you change the policy, once you change the transition metrics, because you have you can visit more states, then you're not going to essentially the prediction that you will let you go to other regions that you have not explored that much to maximize the entropy. So your intuition is correct. So your intuition is like you like a lot of plays, you will go there very often, but eventually you will get tired of it, right? And then you would like to try something else. So this is what this framework will predict precisely.
Okay, but
No, keep asking.
No, because I don't see anything that differentiates for me transitioning from the start to the left side the first time versus the start to the left side on the 10th time, because the entropy is still the same, right?
Yeah, I see your point. Yeah. So this is under stationary conditions in a sense. So like this is like a steady state condition. Okay, so we have this decision tree. So now the nodes are action states, and let's assume that there is a probability of going from ij, pij. So this is a path of length 1, okay? And so let's assume that we perform this transition, and we want to have a measure of the occupancy gain. So how much occupancy we gain by performing this specific transition. I think that this example is going to be helpful for your question. So the first property that we want of the occupancy gain is that is a function of this transition of this probability alone. So if you have experienced this transition a lot, right, then the occupancy gain by performing this new transition is going to depend on that history, on that probability. So if you want this probability is the previous, the empirical probability. Okay? And so that's the first property that you want. The occupancy gain should be just a function of this probability. The second property that you want is that if you perform a transition along the path with the lowest transition probability, which intuitively corresponds to the emptiest path, okay? If the transition probability to this node is 1/7, and this is 3/7 and 3/7, this is somehow the emptiest path. So if I perform this transition, the occupancy gain should be larger than if I perform these other transitions intuitively. So that means that the occupancy gain should be a decreasing function of the probability. So the lower the probability, the higher the occupancy gain. Okay, it's decreasing. The third property is that we want this measure to be smooth, so we don't want to have crazy mathematical quantities here because you can choose like really very crazy quantities if you want. So you want it to be smooth. And now the most important property, which is the additive property. The first thing that we define is the occupancy, which is the average gain, which is just the expectation of the average gain in occupancy multiplied by the transition probability. So that's just a definition. And now it comes the interesting property. So now we're going to move from paths of length 1 to paths of length 2. And we want to use the same measure to measure the occupancy of paths of length 1 and paths of length 2. We want to have to use exactly the same measure. So that means that to quantify the occupancy of paths of length 2, I should use the same expression as before. But now the objects are going to be paths of length 2. And a path of length 2 has probability Pij multiplied by Pjk. And this probability over here. And this is the occupancy gain of this two-step path multiplied by the probability. And that's going to be the occupancy of this path of length 2. And we want that this quantity can be has the additive property, meaning that I can split this the occupancy of paths of length 2 as the sum of the occupancy of the paths of length 1 plus the expected occupancy of the second state transitions, as you can see over here.
For me, it's not clear. Occupancy is a function of what? C is a function that maps what to what?
It's a function that maps probabilities into a number, into a real number.
Okay, and probabilities, for example, I could define the occupancy of the probability of going from this point to that point through any 17 paths? Or like any probability, or?
What do you mean? Like this is a probability distribution, so this is defined over the whole probability, over all the paths in the tree. So this is a priori not computable in real problems. But if there are some inductive biases as to how to estimate this occupancy, then you can figure out what paths, what routes to take. But a priori mathematically, it would be like a measure of occupancy of this Markov decision process
So, but that's what I don't understand. So occupancy is a function of a probability. So I don't have to even think of what events the probability is on.
Absolutely, yeah.
So it could be the probability that you wake up at 9.
Yeah, any kind of state, any kind of Markov decision process.
So it's a property of a probability.
Mm-hmm.
Okay, and if you have discrete events, it's between 0 and 1, the probability.
Right.
So it's a function that maps the interval 0, 1 to a real number.
Right, right, yeah.
Okay.
So that's mathematically what it is.
Okay, so then I shouldn't have to think about paths or anything. If it's just a function.
Well, because I want this additive property. So this is so I want to have a measure where I can split the occupancy generally on any mathematical object that you just said, but I want this to have a specific property, which is that if my object is a Markov decision process, I would like to split this overall occupancy into small pieces. And these small pieces should have this additive property.
So are you just saying that you want a function that is, if it's a function of product, then it's the sum of the functions of each element of the product?
Yeah, that's going to be the logarithm. This is not going to be a surprise.
So that's what you're saying.
Yeah, yeah. Yeah, meanwhile, I can take another question. You can come back if you want.
There's even this thing I don't understand. When you say occupancy of one step path, so if there are like more than one step, you mean like steps forward or like steps like for one layer?
Yeah, here we're considering just paths of length 2, but this is going to be, we're going to generalize this to any length for any path. So this is going to be, so we're going to generalize this. So once you have this property in paths of length 2, you could have this property for free in any path of any length. More questions? Yes.
Here the P matrix is the same.
It doesn't need to be the same here and here. So it can be like a different one. So this is like a hyperformal transition, now you're in a new state, and in the new state you may have a different policy, the policy may depend on that new state, and so on. So remember that because this is an action state, here this transition matrix is the product of your policy with the state transition probability. So you can change that as well. You can change this probability. That's going to be the whole point, that you are going to be able to adapt these transition probabilities, this decision tree. Okay, so I think, yes?
No, does the C function has a form of like minus the log?
Right, that's going to be the only solution, as Robert was pointing to right away. So why the only solution is going to be the minus log? So this is my slide over here. So CP must be minus log of P. That's the only check. So we have the proof of why this happens, although it's intuitively correct. So just for the students, so I'm going to go through this piece of math just to show why the minus log has exactly this property. So let's start. So this is the property that we want. So we want that the occupancy of paths of length 2 has this expression, and this expression can be split into this sum. So let's start with C2. So this is the occupancy. So let's replace C with the minus log. As I'm doing over here. So you know that the minus log, the log of the product becomes the sum of the logs, and I split it into 2 components. And I have this first component and this second component. The first component has a sum over j's and k's. So j's is first step transitions, k's is the second step transitions. So you can sum up over k, because here you have log Pij, k doesn't matter. So then you have this occupancy of just the first part of the path. And here you have this second contribution that is a double sum, but you're going to split in 2 sums. One is the sum over j's, and the second is the sum over k's. And here again you realize that this is precisely again with the minus the definition of occupancy of paths of length 1, but starting in after the first step. So in conclusion, you get that with this functional form, you get the additive property. And there is no other choice. Yes?
What happens if you would have a very small probability of going back, one of the first states you started in.
No problem.
The occupancy would drive you towards these circles?
No, well, in that case, we will need to redefine the Bellman equation that are going to be right away. And then you will need to do like the full loop. Then you're not going to be living in a two-step Markov decision process. You will have like a probability of going back and forth.
But that would be rewarding according to the occupancy?
Yes, yes. If the probability of going back is very little, is very small, if you go back, then it's rewarding. But if the probability of going back or restarting a trial is very high, then that's not very rewarding.
That's the opposite of exploration, is it not?
No, it's related to exploration. So you don't want to go back to situations that are very similar to the ones that you have experienced. So it's connected with exploration, I would say. Yes?
I get how Moreno-Bote is a Bible solution, but why is this thing a Bible solution?
I don't have. I can talk to you plenty of time later on.
Okay.
I think for the sake of time, I should keep moving because the math is in the paper, so we can look at it together if you want. I'm totally happy to do that. There is a proof for this.
Finite number of steps, I can put what I want on the last layer and computer perceiving.
Yeah. It could be anything. It's going to be totally dependent on the Markov decision process. So essentially, the environment is going to tell what the properties of the number of actions that you have available, the possible transitions that you have available, and so on. So the Markov decision process fully defines this Bellman equation. And so let me put together what we have learned. So I define this value function, which is going to be the expectation of sum of feature, action, and state transition entropies. That's going to be my value function. So thanks to the additive property, we can write down a Bellman equation. So we can have a recursion, and that's another advantage of asking for this additive property. So that means the following, that if you want to know the value of being in a particular state under some policy, you have to know the immediate occupancy, so how much occupancy you're going to gain by following a particular policy in terms of action entropy and state transition entropy, plus the feature occupancy. So we can split this idea nicely into a recursive sum using the Bellman equation. And as you know, once you have a Bellman equation, then you can use all the machinery of RL to solve and help you to find the optimal solution, which is very, very handy. So you can find the optimal value function, which is this very nonlinear self-consistent equation. And then you have the optimal policy that is going to be a softmax rule that essentially is going to favor actions that generate high transition entropy. Plus feature occupancy. Okay, so let me give you a few examples.
Sorry, can you why don't you get uniform? What's constraint? I thought you leave the transitions free and the actions free.
Well, this is the state transition entropy.
Right.
So that's given by the environment. So depending on the state and on the action, this entropy can be different. So if you are
what is fixed? Sorry, what is fixed?
What is here?
I thought you maximize over both the transition. So you don't you fix the transition.
Yeah, that's fixed. That's environment, and you optimize for the policy. The only thing that you optimize for here is the policy. So the policy doesn't show up over here, but the fact that you optimize this policy shows up here in the exponentiation. It's a softmax. It's a softmax.
And but this is the greedy solution, or is the?
This is the optimal solution. Greedy.
It's greedy, or it's solving the Bellman equation.
It's solving the Bellman equation. It's the exact solution. There is no approximation here. Yes.
I feel like I understand the lowest level details so far mostly, and the highest level or there's like a stage in between low fuzzy on. If you can get started.
I'm going to give you now a sequence of examples, which I think, okay.
Okay, before examples though, I kind of want to understand the last two slides a little bit better. So, I'm going to get details, but I guess, for instance, we went through this derivation of C quantity.
Yes.
And so we kind of began with this, we did the C quantity, and then we came back to this. I'm a little bit fuzzy on how the C quantity factors into this slide, essentially.
Well,
does that give you H or give you
because this C quantity gives you the minus log as the only choice for that function, the minus log P. And once you plug the minus log P over there and you take the expectation, well, you have these entropies. Remember the expression of the entropies, the minus is the sum over probabilities multiplied by log of the probabilities. And this is what I'm showing over here. So all the math that I'm showing to you in the previous two slides is just to back up this definition, why this definition makes sense, and then connecting with what we have learned in the first lecture. So we can define the Bellman equation, and so on.
So it's sort of a proof and justification of your H.
Right. Because I started, if you remember, with a very hand-waving argument about why the occupancy gain should be the minus logarithm. That was a very hand-waving. And what I'm telling you is that we have like a principal way of deriving this as the only measure of occupancy.
Yeah, quick follow-up question. Make it similar, like the original Shannon entropy paper has a kind of a similar flavor where it says that we want entropy to have these qualities, this form or something.
It's the same spirit proof, yeah. Our proof is in the same spirit. But this is slightly different. If you're interested in that, I can tell you about the differences. But in the spirit is the same. So it's asking a set of properties. Essentially, the additive property is the essential one, and that gives you like a unique form solution to the function.
If you were to give like a one-sentence summary of the differences between like that, maybe I'll actually wait about that. But, first, they had that Shannon thing. You want these properties of entropy, and then you say you want these properties of maximum occupancy. And then, so you're saying it's not the same, right? So there's something different about it.
Yeah, so what's different in the Shannon proof, he assumes that you can have like infinite sequences of random variables. So this is the way he doesn't need to use the smooth condition on the function, because it's interchangeable. And here we don't use that, we don't need to have the infinite sequence of random variables with just a couple. A Markov decision process with just two steps, and the continuous, the smooth assumption, then that's enough to have the proof.
I thought you had the fully enumerable tree though, right?
No, for the proof, not. For the proof, we just need a pass of length 2 to establish the proof, and that's a big difference with the Shannon proof. And then automatically, if this happens for pass of length 2, it's going to happen for any type of math.
So, in principle, the policy could change over time.
Yes.
So the reason you can get a solution that is a full solution is because you fixed it.
It's fixed.
Otherwise, you would really have to solve the Bellman problem. The fact that it's fixed then makes your problem essentially greedy.
Right? Yes. Yes. Yeah. More questions? Okay, so a few examples now. So there was a little bit of math. So let's start the session that you are in this very simple world, where you are in this state, and you have two choices, A1 and A2, that's it. But if you perform A1, there is a transition to a new state that randomly leads to two possible states, S1 and S2. But if you perform action A2, that leads you deterministically to a new state S3 with probability A1. So what is the optimal policy that you should follow to occupy action state space? So naively you could say, okay, it's probability 1/2, right? Because there are two actions, but this is not the optimal one. The optimal one will be taking the top one with probability 2/3. Why? Because here there are two action states, 1 and 2, and here you only have one action state. So a priori, this path is more attractive. Being everything equal after this state. So if everything is equal after that, then this is more attractive. There is no incentive of going into this other path according to this theory. So what if now, if you transition to this state, there's only one action that you can perform, but if you transition to this state, there are many, many actions that you can perform. So which one is more attractive now in terms of like a possibility of occupying? So now the optimal solution will be having a policy that chooses this lower branch with much higher probability than 1/3. The probability is going to depend on the total number of actions that you have available over there. But what if, regardless of the action that you perform over here, you die? Then, if everything is the same over here, so here you can keep continuing, then the agent may realize that going through this path will lead it to an end, and it's not going to be able to generate future occupancy. So that means that the top path is going to be much more preferred than the lower path. Question, yeah?
I feel like if you go to, if you only have a path that deterministically leads you to death, I feel like, shouldn't that just be zero? But mathematically, because it's additive, you wouldn't get a zero.
But it's going to be very small, yeah? Now depends on the number of actions that you have over here compared to the future action state occupancy that you can gain by these actions.
Right, but even if you get like a bunch of possible actions, if it leads you to something with no more possible actions, I feel like it shouldn't matter how many intermediaries, right?
To avoid this path.
Yeah, to avoid that path. Like it should cross zero.
No, your intuition is correct. I mean, in any realistic Markov decision process, this is going to be crazy. I mean, like the possibility of getting to a terminal state, there are many, but there are not too many. So, and you have warning signals when you're getting close to this terminal state. So this is what I said about the nature giving you this built-in signal that will warn you about not going to a specific path. Let's assume that this is like low glucose in your blood path. You're going to have warning signals way before you die. Okay? And these are built-in signals that I think are going to be very important to avoid to have to reason about these huge decision trees. Okay? But that doesn't mean that the nature is not solving, in a sense, these decision trees. But the only thing that I'm saying is that nature at different time scales is solving this kind of decision trees, so that the agents will generate all very complex behaviors and occupy interesting states. Yes?
So I got a question. So you define the function C, which is inverse with respect to the probability white. So
It's decreasing.
In this case, for one step, you get very small probability of A to that's not lead to the agent to make that action.
With very little probability. I mean, if there are like very strong warning signals, then you look, this is really very dangerous path. But as we know in nature, there are individuals that they take really very risky paths from time to time.
So that means sometimes the C is very high.
Yeah. Sometimes specific individuals will have like large rewards by performing this kind of risky options. But they're to try to avoid as much as possible this risky actions. Okay, another example of increasing complexity. So now we have a mod agent, the one that is trying to maximize occupancy, and we have a reward-seeking agent, a traditional reward-seeking agent. Yes?
Yes, sir, I have a follow-up question about the
The previous?
Yeah, just to make sure I understand it.
Yes.
You actually change your diagram a little bit. So under state 3, maybe action 5 leads to a terminal state, but other actions are fine.
Otherwise, yeah.
Yeah, so will that lead to a decreased value to get to state 3?
So you mean like if here there are some actions that keep you can continue living?
Yeah.
Then this is going to increase a little bit the probability of this lower action. But that depends on how easy for you is to escape from this terminal state. If once you get over here, it's very easy for you to escape, or with very high probability you're going to escape, then you may take this other path. So in a sense, you can be risky sometimes. Like explorers will go to Mars, they're going to take the risk by taking this ship to go from Earth to Mars. Bad things can happen, but once you get to Mars, then you're going to have plenty of opportunities. Right? You see my point? Okay. But most of the people won't do that, right? Most of the people won't like to take those risks. Okay, so this is a reward-seeking agent and mob agent. So let's see now the stark differences between the results that you will observe if you model behavior with either of the two approaches. So the agents are identical. So the agent is this little triangle that lives in this four revolve. There are food sources on the corner. And the state of the agent is characterized by the position, x, y, so this is fully observable. And also there is an internal state of the agent, which is the energy. And here, internal states are going to be very important to shape the behavior of both agents in general. So both agents are identical, but the big difference is what the goal is. The goal of the R agent is to maximize some extrinsic reward function. And here, to be able to compare, I'm going to be using a reward function that is going to be just one whenever the agent lives. The reward function is not going to be just consuming food, because otherwise it will be too boring, too easy for me to beat this model in terms of like so this guy wants to survive. Pretty much like the mob agent will let you to occupy a space to perform action state paths, which means that it's going to try to survive as well, because otherwise they won't be able to generate action state occupancy. So in that level they are very similar. The other thing that I'm going to match is the lifetimes. So I'm going to add a little bit of noise to the R agent, so that epsilon greedy noise, as we have been using in some, we have been seeing in some lectures, to generate a little bit of variability, because otherwise it will be very boring agent. And at the same time, this allows me to match the lifetimes of the two agents. So the result, the difference that you're going to see, they're not going to be explained by the fact that this is more risky or this is less risky and so on. Both of them, they live for the same amount of time, okay? So let's see what the reward-seeking agent does. Okay, it looks like a good model of depression. And now let's see what the mob agent does.
Can you say again what's this energy function?
This energy, yeah, I didn't explain that well. So whenever the agent goes to the food source, it gets a boost of 10 units of energy. Whenever the agent is moving without outside the food source, gets lost 1 unit of energy. If the agent knows that if the energy goes to 0, it's going to die. So both agents want to avoid this terminal state of 0 energy. So from time to time, they will go to the food source to get replenished a little bit the energy.
But, sorry, just clarification. So on the right, there's no.
Let me go back to see the. Yes, please.
So R is not affected by the food itself.
Both are affected for in the food, but just as an internal state. So there is this internal state that tells how much energy the agent has on any given time. And the only way this agent is going to work for food is whenever the energy goes to really very low. Well, this other agent is going to work for food because it wants to play very safe, because it knows that it has some noise, and it's going to play very safe. It's going to stick here on the corner and not move much, and then being sure that the energy is always very high. So in terms of behaviors are very, very different.
What I understand is when the energy drops to 0 on the right, does that mean that just the entropy goes to 0, or it means that you have a loss of minus infinity?
The entropy goes to 0.
But you also have a loss of minus infinity?
No.
It's something that you always avoid?
In either case, we have that minus infinity.
So it can happen that you die?
Yeah. Eventually both die. Both agents die. Even if they're following the optimal policy, because there is an intrinsic stochasticity, there is no way of not dying with some probability. Okay? This agent will do exactly the same. So if you just look at kids playing in the playground, it would look more like a So it looks pretty much like a kid playing in a playground, and only when it's really very starving, you can see here, it will go to the food source. I mean, this is like kids playing in the playground, forgetting about everything else, but just moving around and doing all the other stuff. So it looks more realistic in some sense. So this is just to show you that the same result holds for a broad range of parameters. So I'm not picking up or cherry picking the parameters for you. So this is an example that I like a lot. And it's very, very, very simple, very stupid. So this is a reward-seeking agent, the mouse, and this is a mob agent, the mouse again. So there are two types of agents here. The arenas are identical. The agents know that they can die because of two different reasons now. They can die because the energy goes to zero. So that means that they have to go to the food source from time to time, at least, to get this energy boost. And they know that it can be caught by the cat. Okay? So now this agent is going to try to maximize reward every time that it's alive. So reward of 1 for every state and action. And this other agent is going to try to maximize this cumulative sum of action and state and action. So let's see what kind of behaviors do we get in these two agents. So the reward-seeking agent is smart because it's able to learn this strategy of teasing the cat, going here, teasing the cat, and performing this clockwise rotation. So it discovers this escaping strategy to avoid the cat, and at the same time release from the cat this area and harvest the cheese. But it's repeating this strategy ad nauseam. Okay, so smart. So let's see what the mob agent does. So the mob agent initially discovers the same strategy, so it's teasing the cat in the same way. It's a little bit more playful and it looks more risky, but it also discovers this other way of escaping from the cat. Okay? So this animal, this agent, discovers a broader repertoire of behaviors to achieve the same goal. Well, the reward-seeking agent is performing again and again the same strategy. So this is quite interesting for several reasons. The first reason is that these strategies, they were discovered by the agent. So they were not built into the algorithm, it was discovered. This agent is going to be way more robust than this other agent to external predators because this agent is more unpredictable in the free strategies that it has. While this other agent is very predictable, it's always doing again and again and again the same. And if you have noticed, these agents are very smart. So this agent is capable of deterministic behavior. It's capable of thinking, okay, now it's time to tease the cat in this corner so that it's going to chase me. And it's able to do this. But once it has achieved the goal of escaping and having enough energy, it's playful. It's showing energy and moving around and all these kind of things. So this is just to show that the reward-seeking agent has this very deterministic strategy that you can show right away in the transition metrics, in the transition probabilities in Arena. Well, the mob agent is all over the place. There is no clear structure in this map. So this is general for a broad range of parameters. I have to talk about the flexibility of these agents to switch between deterministic and stochastic transitions. So this is the video that I've shown to you many times now. So this is a card pole that it's essentially it's a card which has attached this pole, and there are two different types of terminal states in this case. So the agent will die or will terminate if the card pole hits the walls, or if the pole is beyond 45 degrees. So two different ways of that. We're going to compare reward-seeking agent with the mob agent. So reward-seeking agent solves the task. Not surprisingly, we have a little bit of noise to be able to compare with the mob agent. But so this is before that. So this is the mob agent, which generates a much interesting kind of movement, which can be even dubbed as dancing behavior. So this is Nova dancing tango, and this is me dancing. So Nova is a mob agent in this case. And when you look at the occupancy of interface space, it's totally different. So this is much broadly occupying space of the case. So we can go to very complex agents, and where we cannot simulate these in discrete space, discrete actions. So this is continuous space, continuous action, tens of degrees of freedom, and so on. Things work nicely over here as well. So this is the epsilon greedy agent with no rewards. So it doesn't know what to do unless you tell this agent what to do. It doesn't do anything. But the mock agent, even if you don't tell anything, just move around. That's the only instruction. So generate action state entropy. It generates very interesting behaviors. It's learning to jump, to raise legs, to spin there a little bit, take bows and everything. So we think that this is going to be an interesting and important generative model of behavior. So because it is able to generate all sorts of so I'm going to skip. So how much time do I have? Almost nothing, right?
2 minutes.
2 minutes, okay. So what should I do here? I'm going to skip this because this is another example. This is with empowerment, and the guys yesterday, the empowerment team, did an excellent job. So I don't need to go here. So neural variability. So let me go just briefly about neural variability. So I'm going to skip this. Thing. So Monk provides a new hypothesis about how the brain should work. So remember, here the objective of the agent is generate complex action state transitions, so generate complex behavior. And of course the brain is in control of that behavior. So that means that an important implication is going to be that the brain should generate all sorts of action state transitions, internal transitions, so as to generate interesting and complex behavior. So that's the hypothesis. So that's the hypothesis. Variability is the result of the brain trying to occupy internal space, activity space. This is going to be an account of why we see that much neural variability in activity. But that has very important implications. One important implication is that if the goal of the brain is to generate all sorts of activity patterns, this comes with a risk. And the risk is that these activity patterns from time to time can get close to very dangerous terminal situations. So for instance, like epileptic births and so on. So how do we model this? So this is a recurrent neural network with highly nonlinear dynamics, strong connections, large number of neurons. If you simulate this, and I think that many of you have experience about this, I'm going to plot here the activity as a function of time for these neurons in this chaotic dynamical system, and you will see this type of behavior. So activities of the neurons going up and down in a very stochastic manner. So let's assume for simplicity that having this very high activity is bad. So going above 0.9 is bad because this gets close to a terminal stage with just because you consume a lot of energy. Also, it's bad because it leads to saturation, and then you cannot encode sensory stimuli when you reach this saturated state, and so on. So let's assume that this is a bad state that we want to avoid. But at the same time, we want to generate a system that generates a lot of variability in between and occupies space as much as possible. So what we're going to do is to control this recurrent neural network with a controller that is going to be a mob controller. It's going to be a controller that injects currents with the maximum possible entropy on the long term. So essentially, it would like to generate a lot of variability in this neural network while avoiding these terminal states. This is just math to tell you a little bit how we do this. So I'm going to show you the results, and with this I'm going to conclude more or less. So this is the uncontrolled chaotic recurrent network. So it does this explosion of activity, which we consider it to be not good in this case. So now let's see what the controlled chaotic recurrent network is able to do. So initially, it dies in the sense that the activity hits the threshold, but eventually it starts to learn slowly and occupy more space in terms of like a repertoire of activity. From time to time, it's very risky, as you can see. The activity gets really very close to the terminal state, but without crossing them. And essentially, the network is able to generate more and more complex activity patterns as it's learning through experience with the dynamics of the system. And of course, we can see that the variability increases, learning increases, and so on. Okay, so let me conclude. I'm going to skip all this. And this is, let me conclude with this. Okay, so I have started my presentation asking whether we are utility maximizers. So I have introduced MOP as a way to generate interesting behavior. So external rewards in this framework are still important. As you have seen, goal-directed behavior emerges naturally in these agents. So remember the example of the cat and the mouse. So it looks that the mouse has a goal-directed behavior like escaping, going through to get food. But essentially, there is just one principle that explains all these behaviors at once. It's just the needs of the agent what determines what is going to be chased at a particular time. We have seen that this is a possible account of neural variability. And let me conclude with this, and this is just the final design. So why do I think that this is a general principle of not only about neuroscience, but of organization in general? So if we look at the variability that we see at many different levels, going to biomedical diversity, biochemical diversity, neural activity variability, the diversity that we see in the goals of natural agents, individual traits, and the variety of species, I don't think that we have right now a good way of understanding why we have this huge variability, huge stochasticity apparently in every single domain that pertains to that. And one possible account is this, is like essentially all these systems are designed to occupy space, to exist in time and in space. And the underlying principles that guide all these systems should be principles that play smart in this game, meaning that you want to occupy space not in a greedy manner, not being just very greedy right now. You have to think about things that do right now, that you can do right now, and predict the consequences of the future. So I think that this is going to be an overarching theme for several levels of organization. And with this, I think I'm out of time, so I'm going to stop here, I guess, right?
Yes.
Okay.
One more question.
Yes.
Yeah. One last question.
Professor, what's the difference and the connection between the MOP and soft RL?
Okay, the connection is that the soft RL has been derived and explained just in the context of extrinsic reward maximization. So in all that field, there is always a extrinsic reward function. So there is a clear task that can be winning a game or maximizing sugar intake or something like that. So there is a extrinsic reward function. So this literature, and of course, so they have used soft RL in a way to regularize the problem, the learning problem. So the goal is to maximize the extrinsic reward. We know that this is a very tricky problem because typically that reward function is very sparse, so you will get rewards only very sporadically. So you need to have this intrinsic motivation term that push some behavior, push some exploration. But this is just like a regularization term in this literature. And eventually, once you have learned to solve the task, this regularization term goes to zero. So you don't want to keep it. So you just use it just as a trick to solve the problem. So MOP takes the reverse approach, which is saying the whole thing is this regularization term. So with this regularization term alone, and additional terminal states information, so like the structure of the Markov decision process, that alone can generate all sorts of behavior that are consistent with your agent, that your agent is capable of. So I'm interested in this. I'm interested in what type of behaviors an artificial agent or an animal or a human, if you're interested in curiosity, I would be interested in the question of how we can push these agents to keep exploring more in maximizing this exploration, as opposed to embed agents with a very strict explicit reward function that will really collapse the behavior to very, very specific type of behavior that may be interesting from an engineering point of view, but they may not be interesting from a fundamental point of view to try to understand intelligence per se.
We can talk outside.
Yeah, we can talk there, yeah.